Most engineers don't think of springs as interesting components. They're introduced early, treated as simple linear elements in free body diagrams, and then carried forward as implicit assumptions in systems like suspension models, valve trains, latch mechanisms, and vibration isolation. But springs are not passive elements. They are force systems encoded in geometry. Their behavior determines how loads are distributed, how motion initiates and terminates, and how energy is stored and released under constraint. In practice, a spring often defines the boundary between controlled motion and uncontrolled impact. Once you view mechanical systems through that lens, springs stop being background elements. They become primary design mechanisms that shape system behavior at every scale. Understanding spring design is about recognizing which geometries produce which force displacement behaviors and which trade-offs those behaviors implicitly enforce. Here are 6 spring systems that define how mechanical engineering actually works in practice. The coil compression spring is the most fundamental elastic energy storage device in mechanical engineering. A helical wire, loaded axially, produces an approximately linear force displacement relationship governed by wire diameter, coil diameter, number of active coils, and shear modulus. The governing constraint is shear stress distribution along the wire cross-section. The highest stress occurs at the inner fiber of the coil, not the centroid, which creates a persistent fatigue hotspot under cyclic loading. The key design parameter is the spring index, the ratio of coil diameter to wire diameter, too low, and stress concentration increases due to tight curvature, too high, and the spring becomes increasingly susceptible to lateral buckling and loses manufacturability control during coiling. Another hidden failure mode is solid height contact. When coils touch, the system transitions from elastic behavior to a rigid stack, producing a near-infinite stiffness discontinuity. In dynamic systems like valve trains or suspension units, that transition is catastrophic because it converts a smooth force curve into an impact event. Despite its simplicity, the coil compression spring remains dominant in everything from fuel injectors to industrial actuators because it provides predictable linear compliance in a compact geometry that is easy to manufacture and scale. The extension spring solves a different constraint: tension-based energy storage, with return force under separation. Unlike compression springs, extension springs are manufactured with initial tension. The coils are tightly wound so that a preload force must be overcome before separation begins. This preload defines the usable force range and eliminates slack behavior at low loads. The most critical design limitation is the end geometry. Hooks, loops, or machine-formed ends introduce abrupt stress concentrations that often govern failure long before the coil body reaches fatigue limits. In many cases, the wire does not fail in the helical section at all. It fails at the transition into the hook. Another constraint is overextension beyond the elastic limit. When the spring is stretched beyond its elastic range, coil pitch increases non-linearly until plastic deformation begins. Unlike compression springs, extension springs rarely have a clean, solid height equivalent. Failure is progressive and localized. This is why extension springs are typically used in controlled displacement environments such as throttle returns, latch mechanisms, and industrial tensioning systems where maximum extension can be mechanically limited. Their value lies in simplicity. They generate restoring force in pure tension without auxiliary linkages or guide structures. The torsion spring stores energy in angular deformation rather than linear displacement. A straight wire or helical form resists rotation about its axis, producing torque proportional to angular deflection. The governing constraint here is not axial stress, but combined bending stress along the wire length. Each segment of the spring experiences varying curvature depending on coil geometry and load direction, producing a distributed stress field that is highly sensitive to boundary conditions. End geometry dominates performance. the legs of a torsion spring act as levers, and small changes in leg length significantly affect the torque deflection characteristic through the effective lever arm. Unlike linear springs, torsion springs are inherently coupled to their mounting structure. Misalignment introduces parasitic bending loads that shift stress away from the intended torsional mode into mixed mode fatigue, significantly reducing life. Despite this sensitivity, torsion springs are essential in systems where rotational energy storage is required without gears or couplings, hinge mechanisms, rotary closures, and counterbalance systems in mechanical assemblies. Their defining characteristic is not linearity, but controlled angular compliance in a compact envelope. The Belleville Spring, or disc spring, exists to solve a different problem entirely: high force in minimal axial space. It is a conical washer that flattens under load, producing a nonlinear force displacement curve that can be tuned through geometry. Thickness, cone angle, and inner to outer diameter ratio define the stiffness profile. The key design constraint is nonlinear stability. As the disc approaches flattening, the system can exhibit regions of negative incremental stiffness depending on geometry. This creates snap-through behavior if not properly constrained in stacked configurations. Stacking Belleville washers in series or parallel allows engineers to synthesize almost arbitrary stiffness curves: high force with low displacement, low force with long travel, or progressive multi-stage compliance. However, stacking introduces frictional hysteresis between contact surfaces. This friction is not a side effect. It becomes part of the system response, producing energy dissipation that complicates precise force control. Belleville springs are therefore common in bolted joints, preload systems, and thermal expansion compensation assemblies, where controlled force retention matters more than smooth, dynamic response. Their function is not elasticity in the classical sense, but geometric force shaping under axial constraint. The gas spring stores most of its energy in compressed gas rather than elastic deformation of metal. A sealed cylinder contains pressurized nitrogen, with a piston converting volume change into force output. The governing relationship is thermodynamic, not purely mechanical. Output force is determined primarily by gas pressure acting over the effective piston area, with pressure varying according to compression ratio and temperature. This introduces a fundamentally different constraint: thermal sensitivity. Gas springs change force output with ambient temperature due to ideal gas behavior, making them less predictable than metal springs in tightly controlled force applications. Sealing is the primary failure mode. Seal wear introduces gas leakage, which slowly reduces preload force over time. Unlike mechanical springs, which fail through fatigue or fracture, gas springs gradually lose pressure over service life. Another constraint is velocity-dependent damping. Internal flow through orifices introduces nonlinear resistance, which can be used intentionally for motion control, but complicates pure force modeling. Gas springs are therefore used where smooth, assisted motion is required. Hatchbacks, adjustable seats, industrial lids, and ergonomic mechanisms. Their value lies in force modulation and damping in a single integrated component. The constant force spring is a flat strip of pre-stressed steel wound into a coil that exerts nearly uniform force across its extension range. Behavior comes from elastic bending of a pre-curved strip, which attempts to return to its original radius of curvature. Unlike coil springs, force does not scale linearly with displacement. It remains approximately constant until near full extension. The governing constraint is material fatigue under repeated bending along a single radius. Unlike helical springs, stress is concentrated along a narrow band that experiences cyclic flexure with minimal redistribution. Another limitation is storage geometry. The spring must be wound tightly in a housing, which introduces contact friction between layers. That friction contributes to hysteresis and can destabilize force output in precision systems. Constant force springs are widely used in counterbalance systems, cable retractors, and motion assistance devices where a uniform resisting force is required regardless of extension length. Their defining advantage is not energy density, but force invariance over displacement. What these spring systems share is that their behavior is encoded in geometry and material state. The coil spring encodes linear compliance through helical curvature. The Belleville spring encodes nonlinear force through conical instability. The gas spring encodes force through thermodynamic pressure. The constant force spring encodes invariance through pre-stressed curvature. No sensors, no controllers. Springs do not rely on runtime feedback. Their behavior is fixed at design time. Understanding where this behavior comes from and where each system breaks under stress, fatigue, or instability is what separates component selection from actual mechanical design. If you want to think in those terms, this is Engineering Manual.